So in this talk, we want to present to you how to conduct machine learning model development. And in particular, when you're doing, for example, exploratory model development on a single host Python environment, and then you want to scale it out on all of your data on a distributed environment without actually having to rewrite your code in to move between these steps. So if we take a look at model development and the steps involved in this talk, we're not going to cover feature engineering and feature pipelines and model serving, but we can roughly group it into 4 steps. These 4 steps usually involve some kind of exploration of the data. You build a first draft of your model to find a classifier that you want to use. And once you're happy with that, you would go into an experimentation phase where you evaluate a lot of different trials on multiple machines until you found a good hyperparameter configuration for your model. And then you would probably do some validation, drop some components of your model to see how much value it actually adds to the final model. And then once you're happy with it, you would scale this and train on a lot of resources on a distributed environment. So, but the problem is to move between these steps, you actually have to rewrite your code. And in particular, when different distribution contexts are involved or different setups. So you might do the experimentation on a multi-host environment, on a single host environment, but the experimentation on a multi-host environment. And that leads to a lot of artifacts and non-dry code. So you will repeat the code. You will add, depending on which machine learning framework you're using, you will add config files, which is really hard to track. And the problem gets even worse when you start to iterate on your process and go back and repeat a previous step. Basically, the amounts of artifacts will double. So the open source community has developed a lot of nice tools to tackle this problem, like MLflow to track your experiments, or TensorBoard to track the results of your training processes. But in fact, they don't really tackle the problem at the root of the cause. And so what it's really like, it's a pain. And Jim is gonna talk about the root cause of this problem.
Okay, so this is a software engineering problem primarily. And the issue at play here is that when you develop some code to begin with, you might have a small subset of the data. You'll have it on your laptop. You'll write a notebook or a small Python program. And if you're running on a notebook, you might use a Jupyter kernel. And then is when you decide, okay, I'm going to move into experimentation phase. I'm going to work on a larger amount of data. I have a model design. There's this, if we look at the diagram that Mart's presented, we can see there's this assumption that you're moving forward, that you're always going forward. We're going to try out different hyperparameter combinations. Then we'll do an ablation study to understand the effect of the different components in my model on the final accuracy of the model. And then I'm going to train on the huge amount of data in distributed model training. And then I'm going to be done. But it's never like that in practice. We always have the need to go back. We may decide that we need to add a new feature because the final accuracy is not good enough. We may decide we need to drop features. We just may decide we need to add new regularization components. And this continual process of iterative development basically means you need to move through the 4 different code bases that Mars presented. Now, not everyone will have all those 4 code bases. You may skip ablation studies. You may just have typically hyperparameter tuning. You will typically also work on the small subset of data. And if you have a large enough problem, you might have distributed training. In this case, we mean data parallel, synchronous stochastic gradient descent. But even if you don't have all of the phases, models are getting bigger, data sets are getting bigger, and distributed deep learning in particular is becoming a very important technology with which to develop models. So we know what the problem is, and we know there's a software engineering issue which is related to how do we move between these different phases. Now, currently, these different phases, and we have the first one marked down as EDA, or exploratory data analysis, you'll have some Python code in your notebook, for example. and maybe you don't factor your code particularly well, and you have a training loop and you have the model creation, the data set generation all scattered around your code, and you go to hyperparameter tuning and you say, I'm going to rewrite it. And we have a different shape there representing that really it's going to be a different code base. And the same goes for parallel ablation studies if you decide to include them, and for distributed training. So if you're going to rewrite your code and we don't want you to do that, what are we going to do? So we thought about this quite deeply, and we came up with a new abstraction that we call an oblivious training function. And what an oblivious training function is a piece of core training code that we would like to be unchanged between all of these 4 phases. So this core code is the core code that you're going to use to create your model, to get your data set, your samples, to compile and train that model. And we want that to be unchanged across all of the phases. And the benefits of this obviously will be that we'll enable iterative application development. So moving from distributed training back to your laptop to add a new feature should not be a big problem. So the oblivious training function comes from this idea of transparency, that it should be transparent to the application when you're running it as to whatever phase you're running this code in, this oblivious training function in, it shouldn't care about whether it's running on your laptop or whether it's running in a cluster. It should be transparent to that code, or oblivious. Now, the challenges we have in doing this, because if this was an easy thing to do, somebody would have done it already, is that for every different machine learning framework, they introduce different concepts and libraries with which to go through these different phases. So how do you do distribution? How do you parallelize experiments? How do you do, for example, collective ordered use if you're doing distributed deep learning? I can give the example of TensorFlow because the work we've done to date has been with TensorFlow and Keras. And in the TensorFlow, if you're going to do distributed deep learning, so data parallel deep learning, you have to set up an environment variable called tfconfig with the IP addresses of all the workers. We have to decide on the distribution strategy. If it's collective ordered use, for example, that would be one distribution strategy. When we share the data set for training, how do we share it amongst the workers? Do we have a distributed file system available? And then if we're working with Keras or the estimator framework in TensorFlow, or if we have custom training loops, how do we integrate all this? So what the framework needs to do is abstract out these different components that you have in your existing machine learning frameworks so that the core oblivious training function remains unchanged between the different phases.
So if we take a bigger picture and look at where deep learning is actually headed and how we can make use of this oblivious training function to keep our code transparent, we need to look at we can look at recent adoption of machine learning frameworks like Keras and PyTorch and why they're actually so popular among data scientists. And the main reason of that is that they're very productive and they're high level. And you can also see that by TensorFlow using Keras as their main API now in TensorFlow 2. And these high level productive APIs, they help us really to go from an idea, implementing it quickly and coming to a point where we can start experimenting. And from that point, it becomes a bit more blurry. So you need to take into account the infrastructure that you're going to run these experiments on. For example, we use Hopsworks, an open source platform that we're developing. You can use Spark on Databricks. You can use pure Apache Spark, or every cloud provider has some kind of product to tackle this. And then once we get the results of our experiments, then is actually the point where we should use tools like MLflow and TensorBoard to visualize our results, track the results, and basically iterate faster on our ideas and be more productive in our iterative development. So the question is, how do we keep these high-level APIs and how do we keep them transparent and productive? As Jim has already said, what is actually transparent code? With transparent code, we mean that when you develop a model in just pure Python, standard Python, we want to scale it out on Apache Spark or any other execution engines without having to do any changes to the core code of this model. And so to do this, we need to realize that there are a few building blocks that we need. And the first one is that we need to see what is actually the distribution context that we're in. The single host environment explains it pretty much itself. It's our single host Python environment that we know. Then when you move to experimentation, such as hyperparameter tuning or ablation studies, it's actually a parallel multi-host environment where we train a lot of models in parallel, but they are independent of each other. So there's no communication between those models needed. And then when we move to distributed training, it's actually distributed multi-host where we need some kind of coordination or communication between the workers. And we typically use a ring all reduce algorithm to achieve this communication. And the second part to realize the oblivious training functions are a few core model development best practices. And we've seen the communities already starting to adopt these. And with that, we mean you should encapsulate your model generation code in a class or in a Python function to return that the model such that you can actually parameterize this function and change the model according to, for example, hyperparameters. And the same for the data set. You want to encapsulate it in a class or function such that you can later on just simply switch it out with other parts. And then last but not least, you need some kind of training logic to describe the core training loop, or let's say the stochastic gradient descent optimization loop. And then we have one other tool available, which is the usage of callbacks that allows us to hook into the training loop at runtime to intercept it or get more information out of it when we need it. If we have these two concepts at hand, then we can actually let the system take care of a lot of the complexities involved with distribution and make our code transparent. And with that, I mean in the single host environment, that is, for example, just fixing the hyperparameters and launching the function. In parameter tuning, it's just launching the trials or the functions with different parameterized instantiations, generating new trials from old results, and collecting and logging the results. And in distributed training, it's things like setting up the TF config, wrapping the model in a distribution strategy, and launching the workers in their different roles for the distributed training. So last year at Spark Summit, we introduced Maggy as a framework for hyperparameter tuning on Spark. And today we want to make Maggy a bit more general and allow for these oblivious training functions to be executed in different distribution contexts to make our model development transparent. And we do so with HopsWorks. We won a few prizes with HopsWorks. It's all open source, so you can go and get started yourself with Maggy and HopsWorks. Just to recap quickly, Maggy allows us to schedule machine learning trials on Spark asynchronously. That means we circumvent the synchronization barriers at the end of stages in the Spark synchronous execution model, and thereby we don't waste as much compute. And we do so by blocking the executors with very long-running tasks and allowing for some communication between the tasks and the driver, and thereby we are able to run multiple machine learning trials in the same tasks. And therefore we have asynchronism, saving resources. And today, what we're introducing is that also not only these tasks are asking for new trials when they finish training a previous one, but they can also register with information with the driver such that the driver can send information and set up the distribution context before launching the training function on these workers or on these executors. And so if we look at the API, really what we want to have is we have this training function, and this training function is just a pure Python training function without any further modification. And we just launched, and the training function is going to be launched through a Python library through Maggy. in the different contexts without doing any further modifications. And by doing so, you can actually move between single host and multi-host really easily, because you can always just take the Python function and execute it in a Python kernel as you would normally do. And the demo is going to demonstrate the minimal code changes you need and the best practices you need to follow to achieve this level of transparency. So now I'm going to demo the oblivious training function and show you how all of this looks like in terms of actual code. To do so, I started a HopsWorks cluster. If you want to try it out yourself, you can create your own instance on hopsworks.ai. I created a project for this demo, and we'll use mainly the Jupyter service and the experiment service in this case. I already started a notebook server with a Spark session in it with up to 6 dynamic executors, so we have a parallelism of 6. Usually when you want to do model development, you start out, like I said, on a simple Python kernel. So I have a notebook and it's a Python kernel. And I just took an example from the Keras website for an MNIST model. Luckily, it was already refactored to be according to our best practices that we need in order to be able to run this as an oblivious training function. So we have a model function containing our model logic, returning the Keras model, a dataset function to return the TF data sets, and then you can do your model debugging or model development by simply getting the model. You can look at the summary, add the training logic, so compile the model, get the data sets, and start training. This is nice in a Python kernel because you get immediate feedback on the progress and on possible errors. So, however, we want to take this model now and move to hyperparameter optimization once you think it's ready for that. So if we go here and we have our PySpark kernel in this time, what do we need to make? What changes do we need to make in order to make use of hyperparameter optimization and this function? So we need some hyperparameters. I'll use the kernel size in this case and the pooling size, and also maybe the dropout rate. And in order to be able to parameterize this model, we also need to add these hyperparameters to our function signature. In this case, the dataset stays the same, so we can just reuse the same function. And now we come to the model logic. All we have to do for this one is to wrap it inside another Python function so that we can then ship this Python function to the executors to be executed with different hyperparameter combinations. So again, we need to add the kernel, the pool, and the dropout to make it parameterizable. And in order to be able to do ablation later on, we also need to make the model function and also the dataset function actually to be pluggable. So the same thing here. We want to be able to replace the model automatically with Maggy, so you need to exchange this for this model function placeholder basically. And again, you need to pass through the hyperparameters, so this works. And the same for the data set. So now we have this fully pluggable and parameterizable oblivious training function. The only thing that's left to do is, since we want to optimize something, we simply return the metric that we want to optimize, in this case, the sparse categorical accuracy. Additionally, for hyperparameter optimization, we need a search space, so we define the hyperparameters and the feasible intervals to draw the samples from. And then we can import the experiment module, set a name for this experiment, set the dataset generator, set the model generator, set the context, and pass in an optimizer. In this case, we want to use random search, but we are also working on adding Bayesian optimization. And the search space, and then we can just log on the experiment, which will launch the training function with different combinations on the executors. So while this is running, I'll also explain the ablation study. And as you can see, we get nice feedback over the progress of the experiment inside the Jupyter notebook, so no need to go to the Spark UI. And as you can see, it also features early stopping, which means we can stop poorly performing trials early in order to save resources and try more combinations in the same time. If you're interested in that, I recommend you watch my Spark Summit talk from last year. So yeah, an ablation study. We want to leave out certain components of the model to see what their actual contribution is to that model. In this case, I want to leave out the convolutional layers one by one. And we're making use of a feature of Keras here, which lets you give names to components of your Keras model. So these were defined here. And that will be used by Maggy in order to drop these components from the model. And then when we start the ablation study, we need to fix the hyperparameters to some fixed value. You could fix them to a random value, but in this case, we want to use the previously best hyperparameter combination that was found by the optimization experiment. And then again, we switch the context to ablation, pass in an ablator, in this case, leave one component out. So it will leave one component out at a time, the ablation study object and the parameters that we want to fix. And again, we do a lagom. So now we'll do a quick fast forward until both of these experiments have finished. So our two experiments have finished, as you can see, and we also got all the prints of Keras of the executors inside our notebook, which is nice sometimes to do debugging. The same for the ablation experiment, and I already started the distributed training, and in this case I also just set the context to distributed training, and I pass in a strategy that I want to use. Since I'm using 6 executors, I want to do multi-worker strategy, but also if, for example, if you have multiple GPUs on one machine, you could do a single executor with multiple GPUs and mirrored strategy. And again, I pass in the hyperparameters in order to fix them for the training. This is running on all 6 executors now. And for example, if you would have noticed that something is off with your model during ablation studies or during hyperparameter optimization, if you wanted to go back to a single host environment, is as easy as taking your oblivious training function and just passing in the model function, the dataset function, and a fixed set of hyperparameters and launching it in a Python kernel manually again. So no more changes. So that's how I wanted to show you that you can run the same function in all the 3 different contexts without modifying it. And now you could also get even more feedback from the model training if you wanted to use TensorBoard. For that, we provide the possibility to use the normal TensorBoard callback. And the only thing you have to use is the TensorBoard call module from Maggy in order to dynamically generate the log tiers for each trial within an experiment directory. And if you do that, so now I'm currently running the distributed training experiment. As you can see here, our experiments tab records all of these. Since it's actually Hopsworks launching the training function for you, we can collect a lot of metadata, and you don't have to do explicit logging calls to track your metadata. As we all know, tracking metadata is hard, but this way we call it implicit provenance compared to, for example, explicit provenance if you would be using MLflow, where you have to explicitly call MLflow to log certain parameters. So this is finished already, and these were the 2 previous experiments. One's the ablation loco experiment and the hyperparameter tuning experiment. And as you can see, it records all the trials that were being trained. You can look at the logs that it produced, the metric and the metric that it produced. And we even take a snapshot of the IPython notebook, so you can always go back to that state and check out how your model looked like at that point in time when you trained this experiment. And as I said, you can use TensorBoard. And for example, here I ran an experiment earlier and I already launched the TensorBoard. We're making use of the new hparams plugin for TensorBoard. And again, you can look at your single trials. In this case, I only trained 2 epochs for each trial. You can use this parallel coordinates view to check out which hyperparameters lead to a good accuracy, for example, or you can just normally look at your scalars graphs in the scalars tab for each trial. If you're running a lot of trials, this certainly gets a bit messy, but you can just select the trials that you want to look at, for example, in specific. So yes, this concludes the demo. I hope it was helpful. Let's switch back to the presentation. Thank you. So what's next? Now that we have the oblivious training function and the distribution context, we want to make use of another open source tool, Papermill by Netflix, which will allow us to actually also, even though the code is still in a notebook, we can schedule it in different contexts by simply parameterizing the entire notebook with the context. And then we can, for example, simply take a notebook that's there already and retrain it, for example, if we detected model drift earlier on with another context without having to entirely rewrite our code again for distributed training. To summarize, so what we've shown is that moving between the different distribution contexts actually requires code to be rewritten. But what we want to do is these obtrusive framework artifacts, we want to factor them out such that we really keep only the pure Python code of the model definition. And then we're able to do all the complexities with our framework outside of the scope of this Python code, and let the system handle the complexities for you and the distribution context. And by doing so, we're able to keep actually these high-level productive APIs that we've been working so hard for, and which will hopefully lead to better models and faster iteration on our machine learning model development. Yeah, thank you very much for your attention. Here are the resources where you can get started and how you can reach out to us on Twitter or through the website. And I want to especially thank our team, Sina, Robin, Alex, and Kai, who've also been working on this. Thank you very much.